All right. Describe the shape, the center, and the spread of the ACT scores for Washington. All right. So if we're looking at it, what shape would you call that? Symmetric or normal, right? Okay, so write that down. The shape is normal. Great. Center. Remember, center, we're talking about mean. And if you see the little bitty blue number, like the blue number over here, says the average ACT score, if this is what we're going with, is 16. You see that? Okay, so the 16. The spread is the standard deviation. If you look at the top left, it's the red one, and it says the spread is 5. Okay? No big deal. Easy peasy. So it says we're going to animate this and click to take 5 ACT scores. So we're going to hit animate 1, 2, 3, 4, 5. So it took 5 scores from the population and it averaged them. That's what this blue one is down here. This is the average of those 5. Great. Isn't that handy? So fast. Now, approximate the 5 estimated scores here and estimate the mean right here. So I don't want to go through figuring out what these are, but you can see where the mean fell. It probably is a little lower than 16, maybe? It doesn't look directly under that to me, does it to you? Think around 15? Okay, so let's just estimate the mean as approximately 15. So I could keep doing this. 1, 2, 3, 4, 5, boom. 1, 2, 3, 4, 5, boom. And this is what we were doing by hand the other day, right? But how long would it take to get 10,000 of these? Forever. So that's why we're just going to jump ahead and hit 10,000. Boom. Look, there it is. Handy, huh? Love this little trick. All right, so if you look at this, the blue boxes make the sampling distribution of X bar. How do we know that the sampling distribution of X bar is approximately normal? Well, we knew it was going to look like this because the population it came from looked like that, right? I like to call the population the parent population, right? It was normal, so the little sampling distribution is going to be normal also, all right? So that's what you're writing on number 2. How do we know it was approximately normal? Because the population it came from was normal. All right, that's how you know. That's exactly what we talked about yesterday. And it says, now let's look at the distribution of ACT scores for Montour, whatever, another school. So we're just pretending it's a different school. So we're going to click clear. All right. Change the distribution from normal to skewed. So we're going to change it right here to skewed. Boop. All right. So let's just say this school is skewed right. So notice their average is only 8. Their standard deviation is 6. Okay? Great. What is the shape? Write this down. We're going to be skewed right. What does that mean about their scores? They're generally lower with a few people, with a few of their school student body being able to do well, right? Tracking with me here? Mostly lower scores. But some high achievers is what I'm going to write. Now, we're going to change the bottom 2 drop downs to means. They already say mean. And this one, I'm going to change. Notice my sample size was 5 last time, right? So I'm going to do a really small sample of 2 here. And then on this one, I'm going to do another sampling distribution, but this time I'm going to make it as big as I can using this guy, which is 25. All right? Now, I'm going to save us some time, and we're going to do 10,000. Boom. So notice this. What is the shape here when my sample size is 2? It's still skewed right, isn't it? Still skewed right. So it's same as the population. But what happened when my sample went up to 25? It's pretty symmetrical and normal now, isn't it? So there's something special about that number 25, and actually we rounded up to 30 to say once you get a sample size of 30 or greater, that sampling distribution is going to be normal no matter what the shape of the population is. You can see it here, all right? It's approximately normal. So just for fun, I want to show you something. No matter what, so if I clear this out and I do like a custom, if I do a weird, wonky looking thing like that, right? There's just no name for that. It's just weirdness, right? So what would it look like if I did samples of 2 versus samples of 25? It's still wonky with small sample sizes. However, it became normal when I get big enough. Isn't that crazy? So this translates to really easy justification for a normal distribution when it comes to working problems, because all you have to do is look for your sample size. As long as your sample size is 30 or greater, you know it's going to be normal. Easy peasy. We call this the central limit theorem, and we abbreviate it the CLT. Not to be confused with the BLT. It's the CLT. Okay? All right. Now, looking at your back page, I'm going to switch over. You can see what I'm doing. All right, here we go. When n is greater than or equal to 30, the sampling distribution of x bar is approximately normal regardless of the population shape. Like I said, this is called the central limit theorem, and we do abbreviate that as CLT, unless you really just want to write it out. Knock yourself out. So what does that mean? When you're doing probability questions, you're going to be doing, you have to justify that it's normal first, and then you can do the z-score thing. Remember how I talked about yesterday? It's important to write the formula for the z-score because that's the way the tests are going to look, especially your final. So when you would do that, it would be like x bar minus the mu, the population, divided by the standard deviation divided by the square root of my sample size. So you only have to do this bottom thing when your sample is greater than, just greater than 1, right? The top is going to stay the same regardless if it's dealing with one person or a group of a sample. But if you get to samples, remember how our standard deviation got really small, or got a lot smaller? And that's why, because of this. Table A, we use the norm CDF in our calculator. We don't use table A. All right, that's old school. All right, so looking at a sample problem. Among iPhone users who share their data with Apple, the weekly screen time is skewed right, with a mean of 13.5 hours and a standard deviation of 3.75. A random sample of 100 iPhone users are selected, and the mean weekly screen time of X bar of the samples calculated. All right, so describe the shape of the sampling distribution of X bar for samples of 100 randomly selected iPhone users. So we know the population is skewed to the right, but it's asking us the sampling distribution of all the X bars. What shape would that take on? Normal. Why would it be normal? What did we just say?
It's above 30.
It's above 30. That's it. Yeah. It would be normal because n, which is 100, is greater than or equal to 30. And so I would just say by the CLT. That's my justification, central limit theorem. Because my sample is 100, which is definitely greater than 30, CLT justifies it. Okay? Find the mean and the standard deviation of the sampling distribution. We don't have to do this last part, the 10%, we don't need to do that. But the mean, remember the mean of all your samples is equal to the population mean, which was what in this case? 13.5, yep. The standard deviation of the x bars is the population standard deviation divided by my sample size. So my population standard deviation was 3.75 divided by the square root of 100, which is 10, right? It'll give me 0.375. Now it says calculate the probability that the weekly screen time for the sample is between 12 and 13 hours. All right, so let's draw the picture. Let's visualize what's going on. If my mean is 13 and a half, it's asking me what is this probability that it's between 12 and 13. So I'm looking for this little piece of the curve. When it says find the probability, that means I'm doing a norm CDF question, all right? So we got for 12, so for 12 I would do 12 minus 13 and a half divided by 0.375. 13 minus 13 and a half. Let's see what I get. That's a -4. It's -1.3. Okay. Now, this is all you really have to do as far as the work. But then you would need to show me what you're putting in your calculator. So norm CDF, what would my lower boundary be? -4, you want to use -4? Okay. -4, my upper boundary, -1.3. The mean would be, this is where it's tricky. The mean would be 0, the sigma would be 1. And here's why. Because we use the z-scores. Okay? If we use z-scores in here, then we have to use 0 and 1. You could enter it this way. You could enter it norm CDF, lower boundary of 12, upper boundary of 13, with the mean of 13 and a half and the standard deviation of 0.375. Both of these will give you the same answer. You see the difference here? So why would you do all that z-score work, right? That's what you're thinking. Why? Why would I do that? Well, because that's how TWU is going to test it. Okay, the answer is going to be the same. So if the question is about what is the z-score, you need to know how to get that, right? But if the question's about probability, it doesn't matter how you put it in. You just can't forget how to find the z-score. Fair? So just be careful. If you choose to use z-scores, the mean is 0, the sigma is 1, always. All right? So I don't even know what this comes out to be. Let's see. You get the same answer, 0.0991. 0.091. So that's my answer. Either way you put it in, you get the same answer. All right? There's blankets. It's so far away. All right, now to get you going on chapter 7. We've covered a lot of stuff and it kind of probably feels a little overwhelming. So on the back of your notes or on a scratch piece of paper, let me kind of give you a summary chart of what the heck we've covered. All right? All right, so let me break it down for you as best I know how. So when you read a question, the first thing you're going to want to do is decide, is this a proportions questions or percents or is it in averages? Okay, so I'm going to divide my paper. Proportions or averages? Averages slash means, proportions slash percentages, all right? So, this is how you're going to handle it when the sample size is greater than 1 for both of these cases, okay? When your sample size is greater than 1, so those are things you look for in your reading. First thing it asks for is what is the mean of the sampling distribution? What is the standard deviation? So let's talk proportions for a second. The center of the sampling distribution of all the p-hats is going to be equal to the true proportion given in the question. National survey found that 20% of blah, 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 blah. That would be the mean, all right? The standard deviation with proportions is going to look like this. They're not going to give you a standard deviation in the reading. You're going to have to calculate it, and it's going to be like this. P times 1 minus P over N, and then you take the square root of the whole 9 yards. Then you have to decide, is it normal? You have to prove if it's normal. And the way we prove it's normal, if it's a percents question, is that large counts thing. All right, and that says n times p has to be greater than or equal to 5, and n times 1 minus p has to be greater than or equal to 5. And then to find the probability, we would use norm CDF, like we've done before. Lower boundary, upper boundary, mean and standard deviation. All right, if you're going to use the z-score thing, if you're finding z-score, then your equation would look like this. It'd be the sample proportion minus the population proportion divided by that standard deviation mess we have up here, 1 minus p over n. Now, this is on your chart, I believe. Let me check your chart. I believe that's on your chart. The formula, yep. At the very, so if you look at it, excuse me, the left column, as you look at the left column down, you will see it says standard deviation of p-hat right here, okay? Then it has this, we're not doing that yet, we're not doing this sample size thing yet, but the test statistic at the bottom has that z formula for you. So it's not something you have to memorize, all right? You just need to have it handy. Now, what happens when it's an averages question? Well, the mean of the sampling distribution, the mean of all the x bars will be the population mean. The standard deviation of all the x bars will be the population standard deviation divided by the sample size, square root of sample size. Now, same thing happens here. We have to prove that the distribution is normal without doing all the work, so we have some shortcuts. The one we talked about yesterday is the population is normal, and that would mean that it's given in the question stem, right? They tell me that somewhere in my question. The other method is our favorite method that you found out about today, is the central limit theorem, meaning that n is greater than or equal to 30, right? thirdly, we're not going to really dig into this one just yet, but what if the population is normal? What if my sample's like a size 5? What do I do? Well, in this case, you would draw a dot plot, which because your sample's really small in this case, right? You would draw a dot plot and confirm no strong skewness and outliers. Okay? If there's strong skewness and outliers, then you can't use the norm CDF stuff, but you would just have to prove it by making a dot plot. This doesn't happen very often, and if it does happen, it's usually given to you. So you just have to make a statement of, oh, based on the dot plot, blah, 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 blah. All right? Then, when you're finding the probabilities, we're going right back to norm CDF. All right? The z-score formula for a sample mean would be x bar minus mu divided by sigma divided by the square root of n. That is on your chart as well. All right? So my hope is this gives you a little bit of an organization in your head of what we've done. It is a lot. Do you guys feel like you want to switch the day of the quiz?